Today we're going to talk about axioms. When we talk about axioms, remind us about Euclid created axioms to create geometry. Today we're going to create 4 axioms, not 5. 4 axioms to create a geometry and to show that the O prime is satisfiable. Let's say x is not equal to, if x is not equal to y, what do you expect? X is either greater than y, or y is x is x is less than y, or y is less than x. All right, and let's say x is less than y. That is true. Just let's say that now. That's part of the axioms. And what is axioms 2? I know you cannot wait for axiom 2. Axiom 2 is to just converse. If x is less than y, then x if x is less than y, then x cannot be equal to y. Of course, this is the converse of statement axiom number 1. Axiom number 3, if x is less than y and y is less than z, then x must be less than z. So x is less than z. And axiom number 4 saying that x and y are distinct. How can we say that? There exists 2 point in set C such that x and y are distinct. Now when we talk about any axioms, it's always good to give you a model. So let's give you the model. Is a set contains 2 point, let's say a comma b, and also a operator b. All right, so this is our model. Let's make it smaller and let's write the reasoning. All right, let's write the cases. We're going to write the reasoning in a second, but before reasoning we have to write the cases. We have 2 cases over here. We're going to write 2 more. So what are the cases? So instead of x and y, we're going to use a and b. So you have a less than a, b less than b, a less than b, and b less than a. So there are 4 possible cases, and we assume that let's say if you want, you can think a is x and this is x and this is y. Okay, if nobody can stop you thinking that. Okay, now so that x is less than y is already true. We said that x is less than y. This is true. If this is true, we have to prove that this is false. This is false, this is false, and this is false. How we can do that? And let's do that right here. Okay, let's do it right here. So we're going to prove that a is less than a is less than a is less than a is false. How can we show that? Which axiom is going to allow us to do that? Let's see. Axiom number 2 looks good. A is less than a, then a is not equal to a. Contradict by axiom. Contradict by axiom number 2. Okay, so we just proved that. If contradict with axiom number 2. So if this is false, then obviously this one is false. What remain is b is less than a. We're going to prove that now. So you're going to prove that b is less than a, and let's do it here because we have a space over here. So you're going to prove that b is less than a. So let's see what axiom we can use. Axiom 3 looking good. So if B is less than A, and we also know by axiom 1 and axiom 2, A is less than B. A is less than B is less than A less than B by axiom 3, and then B is less than B, and this one by axiom 2, and by axiom 1, of course. However, this contradict by axiom 2. Contradict. This contradict. So we just proved that this is false. So this is the only statement that holds. Now it's time to do the reasoning. We are good. The axiom 1, axiom 2, axiom 3, and axiom 4. So axiom 1, axiom 4 tells us that the C contains with A comma B such that A is not equal to B. Axiom 1 tells us that X, of course not X, A is not equal to B, so that A is less than B. Axiom 2 tells us that axiom 2 we get it for free, it's converse. A less than B, then A is not B. Axiom 3 tells us that A comma B comma C is a null set. A C says that A less than C and B greater than C. So we would say that O prime is satisfiable by these 4 axioms.